This is my trigonometry course. Today we're going to prepare for the second test of the course. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. I've said it before, I'll say it again. There are some subjects where you can study a night before and get a perfect score in the exam. Math doesn't work that way. You need at least 2 or 3 days to prepare for an exam. But it doesn't matter how many times you tell students to study for an exam, they're not going to do it. So in order to force you to do at least some studying, we're going to do a practice test together right now. And I'm going to give you a practice test for homework. And these tests are not only going to force you to do some studying, but they're also going to familiarize you with the format of the test. Now be aware that you need to memorize these formulas here. And I know that that seems like a big task, but you should have your basic definitions and the special triangles memorized already, and the basic graphs. So all you need to do is memorize these identities, and we're really not going to, there's not going to be any problems on the test that use these identities down here. So you probably don't really have to memorize those. So I know that seems like a lot, but you're going to have to memorize those eventually, so you might as well just surrender to that. And you'll need a calculator for the test. Make sure your calculator is in degree mode. Let's go ahead and get started. It says here, simplify the expressions below. So see if you can do problem number 1. If you get stuck, that's okay. But see if you can do that problem. When you come back, we'll do it together. Okay, we're back. So this is going to be a ratio identity, sine over cosine. So that's going to change to tangent alpha. And over here we have a, we can change secant alpha to 1 over cosine alpha. That is a reciprocal identity. And when we multiply these, we get 1. And tangent alpha squared is the same thing as tangent squared alpha. We're used to saying it in the condensed notation. Condensed because we don't have to write parentheses. And you may recognize this as a, whoops, that should be alpha. Sorry about that. My computer's going slow, so I'm having to concentrate on fixing that. This is a Pythagorean identity, so it turns into secant squared alpha. So there you go. If you got that one right, excellent. Again, the reason we changed from this form to this form is it's just more recognizable. All right, go ahead and try number 2. If you get stuck, that's okay. Remember, the whole purpose of a practice exam is to review the material. So if you're a little rusty on this, that's okay. But try number 2, and when you come back, we'll do it together. Okay, we're back. There's a lot of ways to show this, but here's one way. Remember, a fraction symbol can be interpreted as a division operation. And now I'm going to use a reciprocal identity, actually 2 reciprocal identities. I'm not dividing yet. I'm just changing cosecant x to 1 over sine x and secant x to 1 over cosine x. And now we're ready to divide. So remember, when you divide fractions, you change to multiplication and flip the divisor. And when you multiply fractions, you multiply the numerators. 1 times cosine x is cosine x, and multiply the denominators. Sine x times 1 is sine x. And then we have a ratio identity. Cosine x over sine x is cotangent x. And cotangent x plus cotangent x is 2 cotangent x. So if you got that one right, excellent. So now try number 3. See what you can do for number 3. When you come back, we'll do it together. Remember, if you get stuck, that's okay. All right, we're back. So you don't really have to do this, but I'm going to group sine squared and cosine squared together just because it makes it easier to see what's happening here. And I can go ahead and change 1 plus cotangent squared theta to cosecant squared theta because I can identify that immediately as a Pythagorean identity. And we also see that sine squared theta plus cosine squared theta is 1. I know it's getting kind of confusing with all these highlights here. Cosecant squared theta minus cosecant squared theta, they cancel out, and we're left with negative sine theta. And these 1s are going to cancel out, so we're left with cosine theta over negative sine theta. And once again, we have a ratio identity, so we're left with negative cotangent theta. So if you got that one right, excellent. Okay, go ahead and try number 4. For number 4, we're going to prove that the equation is true by converting the left side to the right. So go ahead and try number 4. When you come back, we'll do it together. All right, we're back. So what we can do here is multiply these two using the FOIL algorithm. So sine A times sine A is sine squared A. That's f of FOIL, and then O of FOIL is sine A times negative 1 is negative sine A. And then O of FOIL, or excuse me, I of FOIL insides, multiply 1 times sine A. And then L of FOIL, last terms, 1 times negative 1 is negative 1. That's basic mathematics. If you're having trouble with that, then I would just tell you that that is something that you should know by now, and if you are rusty on that, then it shouldn't take very long to remember it. If you're concerned that you don't know what that is, then you're probably in the wrong class. Sometimes people try to take advanced courses without fulfilling the prerequisites. That doesn't work with mathematics. Okay, so at this point it's not exactly obvious what to do because it gets kind of tricky. What we have to do is we have to change 1 to sine squared A plus cosine squared A. So we used a Pythagorean identity. And now we can distribute that negative. If we're subtracting that whole sum, then we have to distribute the negative to each term. And you can see that the sine squareds cancel out. And we're left with negative cosine squared A. And you can see that's exactly what we're trying to prove, that the left side equals negative cosine squared A. So if you got that right, good. You don't have to have a big green pen to make that check mark. In fact, the check mark is not really necessary. That's just something to show that we proved that the equation is true. So you want to do the same thing on number 5. If you got number 4 right, good. If you're having some trouble with this, that's okay, because we're reviewing the material. That's the whole point of these review tests. Go ahead and try number 5. When you come back, we'll do it together. Okay, we're back. So this problem typically confuses students. Whenever we factor in upper mathematics, students often, well, if we factor out a common monomial, students really get confused. But this term here has a secant b, and this term has a secant b also. So that's what we're going to do. We're going to factor out secant b. And students sometimes get confused, understanding that factoring is really the opposite of multiplication. If you multiply secant b times this sum using the distributive property, you can see we get right back to here. Secant b times tangent squared b is secant b tangent squared b. Secant b times 1 is secant b, and students refuse to acknowledge that. They just don't like it. But you're going to have to get used to it, because you're going to use that type of factoring quite a bit in the math curriculum. At this point, we see that this is a Pythagorean identity. That changes to secant squared b. I believe we already used that Pythagorean identity once today. Secant b times secant squared b is secant cubed b. And we're done. We proved it. We proved that the left side equals secant cubed b. So if you got that right, good. Go ahead and try number 6. If you had a little trouble with this, that's okay. Students often have trouble when it comes to factoring out a monomial. But now you know. You may see a problem like that. Try number 6, and when you come back, we'll do it together. All right, we're back. So this is actually a fraction decomposition problem. If you have a sum or a difference divided by some monomial, this is actually a monomial, it doesn't look like it, it's one term, then you can take every term in the sum or the difference and divide it by that. That's another way of saying that we can decompose the fraction. So to show that, you don't necessarily have to show it, but this is what it would look like if you were actually to write that concept on paper. We're dividing each term in the sum by the monomial in the denominator that we're dividing the whole numerator by. So we took secant and divided it by the denominator, and we took sine and divided it by the same denominator. So in order to understand why that works, because it is kind of confusing, we usually don't go in that direction. You see that we have a common denominator here, and if we started from here and went backwards, we would just add those fractions up because they have a common denominator. They have that blue common denominator. We could just add the fractions up and get this expression here. So we just went backwards, and again, I know that's confusing, but that's fraction decomposition. Now we're going to cancel out these signs, and we're going to cancel out the secants. Those are common factors, so we're left with 1 over secant beta plus 1 over sine beta minus cosine beta. 1 over secant is that's cosine beta. That's a reciprocal identity. And 1 over sine beta is cosecant beta. That's also a reciprocal identity. Cosine beta minus cosine beta is 0, so we're left with cosecant beta. And notice that that's what we were trying to prove, that the left side is equal to cosecant beta. So if you got that right, excellent. So number 7 is going to be a problem where we have to combine the fractions. So you're going to take the left side of the equation and try to make it look like the right side by combining those two fractions. This fraction here and this fraction here. So go ahead and try number 7. When you come back, we'll do it together. Okay, we're back. So you do have to show some work, but you don't necessarily have to show everything that I'm about to write. This is kind of tedious to have to write this. I'm only doing it to show you exactly what's happening. But I'm going to demonstrate that we're multiplying both sides of this fraction by 1 minus sine x. And there's a number of things that you really have to be careful about. One thing is you need to put parentheses around, I guess I'll do that in red. You need to put parentheses around 1 plus sine x. And then we'll multiply both sides of this equation by 1 plus, or both sides of the fraction, that is, not the equation. Both sides of that fraction by 1 plus sine x. And again, notice that I have to put parentheses. You see these blue parentheses? If I don't write those parentheses, then the expression is not technically correct. Now, the reason that I did that is to get a common denominator, and I can't forget my plus symbol. A lot of students will forget that plus symbol. Do not forget that plus symbol. So I'm doing this to get a common denominator so I can add the fractions up. And I need to distribute the sign using the distributive property. So sine x times 1 is sine x. Sine x times negative sine x is negative sine squared x. And I'll just leave the denominators in the factored form for now, just so we can not complicate things. I'm going to distribute sine x here, so sine x times 1 is sine x, and sine x times sine x is sine squared x. And again, I'm leaving the denominator in factored form, just taking it step by step. So now we're going to add the fractions, and I'm going to go ahead and write all that. Again, I'm showing more steps here than you have to show. You do have to show some work, but I'm showing a lot more than is really necessary just to make sure that you know what's happening. Okay, so we combine the fractions, and as you can see, these cancel out, and when we add the sine x with the other sine x, we get 2 sine x. And now we can multiply the denominator terms, the denominator factors, because there's really nothing else to do. So we have to use FOIL. So f of FOIL means first terms. 1 times 1 is 1. And O means outside terms. 1 times negative sine x is negative sine x. inside term, sine x times 1 is sine x. And outside term, sine x times negative sine x is negative sine squared x. And the sine x's cancel out. So we're left with 2 sine x over 1 minus sine squared x. And again, it may be a little difficult to see where to go from here, but we can take that 1 and use it with a Pythagorean identity. 1 is equal to sine squared x plus cosine squared x. So that was a Pythagorean identity. And the sine squared x's cancel out, and we're left with 2 sine x over cosine squared x. And we'll see if we can make some more room. I need to keep writing my equal signs. And so we're going to factor. I'm going to take the 2 and the sine x in the numerator and one of the cosines in the denominator. Maybe we should write that in factored form just so you can see. So all I did was just factor the cosine squared x. I changed it to cosine x times cosine x because that's what it is. But I can take this part here and use a ratio identity, and I can take this part and use a reciprocal identity. But before I do that, I'm going to go ahead and separate. And maybe I can take this 2 and put it out here just to get out of the way. And over here we have 1 over cosine x. Again, I just chose to write it in a different form. Now, students oftentimes object to this type of thing. And they say, well, I don't know how you can change that to that. Well, again, all we're doing is just going in the opposite direction. If you multiply, you'll get this expression here. 2 times sine x over cosine x times 1 over cosine x is this expression here. We just multiply the denominators and multiply the numerators. But now we're just going backwards. And why are we doing that? Because now we can use a ratio identity here and a reciprocal identity here. And that's going to give us what we're looking for. So let me find some more room. Finally, we have 2 times tangent x times secant x. And we're done. We proved it. We're trying to show that the left side is equal to 2 tangent x secant x. So we got that one right. That was kind of a challenge problem. So good job. Okay, go ahead and try number 8. You're going to need a calculator for this problem. And when you come back, we'll do it together. Okay, we're back. I'm going to add 1 to both sides of the equation. And I'm going to actually subtract tangent theta from both sides of the equation. And I'm going to divide both sides by 11. And we don't recognize this ratio, so we're going to have to use the calculator. And this is the notation that mathematicians have decided to use to tell the calculator what to do. If you're using a TI 84 Plus, you want to push the blue button and then the tan button, and then 16 divided by 11, and then enter. And your calculator in this example is going to give us the actual reference angle, 55.5 degrees. We can round to the nearest tenth. And tangent is positive in this example, so I know that our triangles are going to be in the first quadrant and the third quadrant. So in the first quadrant, the reference angle is the actual angle, and in this quadrant, the angle is going to be, well, the reference angle is the same. It's 55.5 degrees. But the actual angle is going to be 180 plus that number, which is 235.5. 235.5 degrees. So the final solutions are 55.5 degrees and 235.5 degrees. Again, the problem tells us to round off to the nearest tenth. Now, your calculator may give you the reference angle. In this case, it may give you a negative number that's the reference angle, or it may give you a number that's not the reference angle, a number that represents an angle that terminates in the second quadrant. Those are the three situations that you may encounter with your calculator, so just be aware. Sometimes your calculator is not going to give you the actual reference angle. It won't give you the reference angle when you have a negative number here and a secant inverse function or a cosine inverse function. And if you have a negative number here and the sine inverse, tangent inverse, or cosecant inverse function, your calculator will give you a negative angle measure. So if you got that right, good job. Go ahead and try number 9. We have the sine function and the cosine function in this equation, and we can't have both of those because it's too difficult to solve the equation. So we have to get rid of that cosine squared alpha, convert it to a sine squared alpha expression. So try number 9. When you come back, we'll do it together. Okay, we're back. So we're going to change that negative cosine squared alpha to 1 minus sine squared alpha. Now, how can I do that? I can do that because we know that sine squared alpha plus cosine squared alpha is equal to 1. So if I subtract sine squared alpha from both sides, we get 1 minus sine squared alpha on the right. And so we replaced this cosine squared alpha with 1 minus sine squared alpha. So now we're going to simplify the equation. That negative is going to distribute to each term in the difference in the parentheses. That's typically where students would have trouble with signs. This is a positive green 1, so it becomes negative 1. And this is a negative sine squared alpha, so it becomes positive sine squared alpha, because you're subtracting this whole difference, everything in the parentheses. Okay, so now we're going to combine these sine squareds and we get negative sine squared. We'll combine these numbers, we get negative 4. And then I'm going to put the everything on the left side of the equation, because now we recognize this as a equation that resembles the quadratic form. We have a squared function, and we have functions that are not squared, and a regular number. So I'm going to put that sine squared on the other side. And I'm going to subtract 8 sine alpha from both sides. And I'm going to add 4 to both sides. So now this equation resembling the quadratic form is in standard form. And if we try to factor this, we can see that it's not really going to work very easily. Let's let x equal sine alpha. And replace sine alpha with x. If you try to factor this into the product of two binomials, we're going to ask what are two numbers such that when you multiply them you get 4, and when you add them up you get -6. Well, you'll find that there are no easy numbers that fit that those characteristics. So we're going to have to use the quadratic formula. This is a quadratic equation. We have to use the quadratic formula. So x is equal to -b plus or minus root b squared minus 4ac over 2a. So we have -b plus or minus root b squared minus 4 times a times c over 2 times a. So I'm going to move this over a little bit. And now we just have to simplify. So that's a double negative, so it becomes +6. And we have 36 minus 16 over 2. And we have 6 plus or minus root 20 over 2. And so what this means is that we have two numbers. We have x is equal to 6 plus root 20 over 2, or x is equal to 6 minus root 20 over 2. Now remember, if you run out of room, don't panic. We can go up to the top here, and let's use our calculator to figure out those numbers. So 6 plus root 20 and then divided by 2. If you're using an iPhone or an Android phone, then this is not going to be very easy for you to enter this stuff in, but you can do it. We get approximately 5.236 for the first number. And for the second number, we get, let me enter that in, 6 minus root 20 divided by 2, we get 0.7639 approximately. And so that's what x is equal to, but we don't care about x. We want to know what alpha is. That's what we're looking for. And x is equal to sine alpha. So sine alpha is equal to these two numbers. And I've still got this number in my calculator. Notice that we have a number that's bigger than 1. Remember, sine has to be between -1 and 1, so we'll just write not approximately equal to. But over here, we're going to use the calculator, and hopefully you still have that number in your calculator. So we can say sine alpha is approximately equal to sine inverse of that number, and that number should still be in your calculator. So we get 49.81, and the problem doesn't tell us what to round off to. Sometimes problems will tell you what to round off to, sometimes they don't. But we get 49.81 degrees. We can round to the nearest hundredth. And it says to find alpha between 0 and 360. So we're talking about the sine function here. So let's draw some triangles to see what's going on. 49.81 is in the first quadrant. Sine is also positive in the second quadrant. Positive 0.7639. So our reference angles are both the same as usual. 49.81 degrees, 49.81 degrees. Our first answer is 49.81 degrees, but our second answer is going to be whatever this blue arc is, and that's 180 minus that number. So 130. 130.19 degrees will round off. So our final answers are 49.81 degrees and 130.19 degrees. So if you got those answers, excellent. Okay, so on to number 10. Be aware we're looking for all values of omega. So this one's a little tricky. If you get stuck, that's okay. But see what you can do. See if you can come up with any ideas. If you can't, then we'll do it together. But see what you can come up with, and when you come back, we'll do it together. Okay, we're back. So we're actually going to add cosine omega to both sides of the equation. And then we get sine omega is equal to cosine omega. Now you don't have to show this. I'm just showing that because sometimes students get a little confused. And now at this point a lot of students will get stuck. Don't feel bad if you got stuck, because it's kind of a tricky move on the next part of the problem. We have to divide both sides by cosine omega. There's actually different ways to do this. You could actually divide both sides by sine omega also. Cosine omega divided by cosine omega is 1. Sine omega divided by cosine omega is tangent omega. That is a ratio identity. Okay, so now we have a simple equation. We simplified. Up here we had two trigonometric functions, but now we only have one, so it's much simpler to deal with. You may recognize this ratio as x over x, so we can draw, maybe I'll do that over here. We'll draw some triangles. Tangent is positive in the first and third quadrants. Technically those triangles are supposed to be the same shape, but I didn't draw them that well. I guess they're okay. And again, the sides are x and x, or negative x and negative x, and we're dealing with a 45, 45, 90 degree triangle. Of course, it's the old recognizable special triangle. The reference angles are both 45 degrees, so this angle is actually 45 degrees, but the other angle is 225 degrees. So omega is equal to 45 degrees, but omega can be 225 degrees also. But remember, we're looking for all values of omega. So we have to add multiples of 360 to find the measure of coterminal angles. And it looks like we need a little more room here. N is any integer, because we want to add multiples of 360 degrees. And same thing with this this expression here. So that those equations are the answers. So if you got those right, excellent, good job. Okay, so go ahead and try number 11, and when you come back, we'll do it together. All right, we're back. Now we have 3a inside the sine function, and I want to warn you that whenever you multiply the variable in a trigonometric expression in an equation by a whole number, 3 is a whole number, then you're probably going to have more solutions. In fact, you're going to have 3 times as many solutions in this case than you'd think you would have. Normally you would have 2 solutions for an equation like this, but now you're going to have many, many more. So see if you can find all the solutions between 0 and 360 degrees. This can be a very tedious and confusing problem, but go ahead and try number 11. Do your best, and when you come back, we'll try it together. Okay, we're back. So the sine function is equal to negative root 3 over 2, and that's a recognizable ratio. Sine is negative in the third and fourth quadrants, and the hypotenuse is going to be 2x. The opposite side is going to be negative x root 3, just based on the definition of sine. This side is x, this side is negative x. So we recognize this as a 30, 60, 90 degree triangle. The angle opposite x root 3 is always 60 degrees, so in this case the reference angle is going to be 60. So one of our angles is going to be 240 degrees, and the other angle, let's see if we can come up with a different color here. The other angle is going to be 300 degrees. So it seems that we have 2 solutions here, but again, those are not the actual solutions. That's what 3a is going to be equal to. These are the numbers that you can put in the sine function that will give you negative root 3 over 2. But we're not looking for the numbers that you can put in the sine function that will give you negative root 3 over 2. We're looking for the numbers that you multiply by 3 to get those numbers that will give you negative root 3 over 2. Very confusing. So a is not equal to 240 degrees. 3a is equal to 240 degrees. And 300 degrees. So we divide both sides of this equation by 3 and we get our solutions. But this is where things get tricky. We're going to have a lot more solutions than the 2 we get dividing these numbers by 3. A lot more. So we have to keep going. We're going to find the measures of coterminal angles. So I'm going to take 240 degrees and add 360. And we get 600 degrees. And I'm going to take 300 degrees and add 360, and we get 660 degrees. And we're going to need even more numbers than that, because again, the 3a indicates that we're going to have 3 times the number of solutions that we think. So I'm going to take 600 and add 360, and then we get 960 degrees. I'm going to add 660 to 360, and we get 1020 degrees. So I just found a bunch of coterminal angles. These are coterminal. and these are coterminal. So now we're going to divide everything by 3 because we're not looking for 3a, we're looking for a. So I'm going to rewrite all that and divide everything by 3. You don't have to show this step. You can just do it in your calculator. So 240 divided by 3 is 80 degrees. So you see that the number that we're actually finding is much smaller than we thought. That's why there's more solutions. And some of these problems you can probably do in your head. So that's 220 degrees, 330 degrees, and 1020 divided by 3 is 340. And now you can see we're approaching 360 degrees. It says up here we want the solutions between 0 and 360 degrees. So let's look that over, make sure we did everything correctly. Actually, we got a wrong number here. That should be 320. That's why it's good to go back and make sure that you did the arithmetic correctly. Okay, so if you got that answer, good job. If you try to keep finding more coterminal angles and you divide by 3, you'll see that we go above 360 degrees. So I know that problem was kind of tedious, but there's nothing you can do to avoid those types of problems. You're going to get some of those. Okay, go ahead and try number 12. Now, with number 12, there's going to be one solution that you might miss. Just about every student is going to miss this one solution. You'll find some of the solutions between 0 and 360, but you may miss one, so be careful about that. If you miss it, that's okay, but try number 12, see what you can do, and when you come back, we'll do it together. Okay, we're back. So notice cotangent is equal to -1, so we see immediately that's going to be a recognizable ratio, x over x. And cotangent is negative in the second and fourth quadrants. And we recognize this as a special triangle, the 45, 45, 90 degree triangle. So obviously the reference angles are 45 degrees. So this angle is 180 minus 45, which is 135. And then this angle over here is going to be 360 minus 45, which is 315 degrees. Now I know that's kind of a lopsided blue arc there, but we don't really care. We're just trying to demonstrate what the angles are. So it's very important to understand that the red and the blue angles are numbers that you can plug in to this here to get -1. We're not looking for the numbers you can plug in to here to get -1. We're looking for alpha, the number such that when you divide it by 2 and subtract 45, you get the red and the blue numbers. That's what we're looking for. So alpha divided by 2 minus 45 degrees is going to be 135 degrees or 315 degrees. Now, if we proceed from here, we're actually going to miss a solution. So it's very easy to miss a solution. These are very tricky problems. Notice that we're going to add 45 to both sides. And what that means is that we need to write the measure of a a coterminal angle, we're going to write negative 45 degrees also. Now, why are we going to write negative 45? That's obviously not a solution. But again, we're not looking for these numbers here. We're looking for alpha. And alpha, after we isolate it, we might get a number that's actually between 0 and 360. So we're going to add 45 to both sides of the equation, and we get 0, 180 degrees, and 360 degrees. Now you can see that we have numbers. Some of them are between 0 and 360, some of them are not. But before we stop, let's keep going. We're looking for alpha, not alpha divided by 2. So we're going to divide or multiply both sides by 2, and we get 0, 360 degrees, and 720 degrees. So there's only one solution. There's only one number here that even works. 720 doesn't work because that's not between 0 and 360. 360 doesn't work because it doesn't say alpha is less than or equal to 360. It says just less than. But over here it says alpha can be greater than or equal to 0. And you can put a degree symbol on there if you want. So the only solution that we found that really works is 0 degrees. Now you might think, well, what if we try some negative angle measures that are less than negative 45 degrees? Well, if we chose, for example, negative 225, we could keep going clockwise, and we could get negative 225. When we add 45, we're going to get a negative number. You multiply by 2, and we still get a negative number. So it's not going to be within our restriction here. Again, I know that seems very complicated, but this is one of the more difficult parts of trigonometry. Some of this stuff does kind of get complicated. So when you have these expressions inside your trigonometric functions and you're trying to solve an equation, be aware that you may have some hidden solutions. Is that annoying? Yes. Are you going to do the problem anyway? Yes. And be aware that this next problem has no solution, but you have to explain why it has no solution. We can't solve it because we have a cosine function and a sine function, and that makes it too complicated to solve this equation. Also, we have a square here. Actually, we're not going to be able to get rid of that square, but see if you can try number 13, and if you get stuck, that's okay, but see what you can do. When you come back, we'll do it together. Okay, we're back. So we know that sine squared theta plus cosine squared theta is equal to 1. If we subtract cosine squared theta from both sides, we see that sine squared theta is equal to 1 minus cosine squared theta. So we are going to take this and replace it, or take sine squared theta and replace it with 1 minus cosine squared theta. Is that tricky? Yes. But you're going to need to use that many, many times throughout your math education. So at this point, we have a cosine function squared and a cosine function that is not squared and some other regular numbers. And this equation is actually going to be something that resembles a quadratic equation. We're going to add cosine squared theta to both sides and keep the cosine theta at the right. We're going to keep that in its place. And we're going to add 5 and 1. and then put it on the other side. And the reason that we did that is because this is an equation resembling a quadratic. We can't solve a quadratic equation unless we put it in standard form. So let's let x equal cosine theta, and then we get x squared plus x minus 6. Now you should recognize that as a quadratic. You don't have to use substitution if you don't want to. You can actually factor this in your head. So we have to ask what two numbers multiply to negative 6 and add up to positive 1. What are two numbers that multiply to get negative 6 and they add up to 1? The answer is 3 and negative 2. So that equation tells us that x can be equal to negative 3 and maybe we should well, I guess we don't have to. X can also be equal to 2, because if you plug in 2 you get 0, and 0 times whatever that number would be 0. So we know that x must be negative 3 or 2 to make this equation work. But we're not concerned with what x has to be. We want to know what theta has to be. So we're going to change x to cosine theta because that's what we defined x to be. But at this point we see that we have a big problem. Cosine theta cannot be bigger than 1 or less than negative 1. So both of these equations are not possible, and therefore we have no solution. So that was kind of a tricky problem. But sometimes you're going to deal with that situation. Alright, so if you got that right, excellent. See if you can do number 14. If you get stuck, again, that's okay. But try 14. When you come back, we'll do it together. Alright, we're back. So, in order to do this problem, we're going to use the sum formula. So I'm going to change that to sine 210 degrees plus 45 degrees. Now you could do this in different ways. You may change a different sum or try a different sum, and that's okay. This is just one way to do it. So now we're going to use our sum formula. So our sum formula says that that's equal to sine 210 times cosine 45 plus sine 45 times cosine 210. So again, that is our sum formula that we learned. And notice that these are all special angles. Now you can draw triangles if you want, but you don't really have to. At this point in the curriculum, you should have the experience to be able to figure these out really in your head. I know that's a tall order, but you really need to be able to do these quickly. We could draw the triangles, but that would take a while. So 210 is in the third quadrant, and 210 is 30 degrees beyond 180. So the reference angle is 30 degrees, and sine is opposite over hypotenuse. The opposite side of 30 degrees is x, or in this case negative x, and the hypotenuse is 2x, so that's going to reduce to negative 1/2. X over 2x, negative x over 2x is negative 1/2. And then cosine 45, 45 is in the first quadrant, and that is a 45, 45, 90 degree triangle. And we have the same thing for sine 45 degrees. cosine 210. That's going to be, again, in the third quadrant. Reference angle is 30 degrees, but now we want the adjacent side over the hypotenuse. Again, if you want to draw triangles for this stuff, you can. So now we need to multiply the fractions. We're going to multiply the yellow ones, and we're going to multiply the green ones. So 1 times 1 is 1, and 2 times root 2 is 2 root 2. And 1 times root 3 is root 3, and 2 times root 2 is 2 root 2. So both of these are negative, both these fractions. Notice we have a common denominator. We have the blue common denominator. So we can combine these. We get negative 1 minus root 3 over 2 root 2. And remember, we're not allowed to really have an irrational denominator. In some cases, it's okay. But in this case, it's pretty easy to rationalize the denominator. So I'm going to multiply both sides of that fraction by root 2. To be honest, if you left the fraction in this form, I wouldn't really care that much. It's not really that big of a deal, but just to let you know, technically we're supposed to rationalize the denominators. And there you go. If you want to, you can factor the negative. You don't really have to. If you factored the negative, you would get that expression there. So we use distribution up here. And remember, root A times root B is equal to root AB. These are just basic math properties. And down here, we multiplied root 2 and root 2 to get 2, and then the 2 multiplied by this other 2 to get 4. If you need to review the roots, you can go back to my intermediate algebra course, and we cover that. Okay, if you got that right, good job. So see if you can do number 15. 15 is kind of a weird problem. You're going to have to use a difference formula. In the previous problem, we used a sum formula. Now you're going to have to use a difference formula. And also, we don't have any formulas for secant. So you're going to have to use a reciprocal identity. Try 15. When you come back, we'll do it together. Okay, we're back. So secant 15 degrees is 1 over cosine 15 degrees. And 15 degrees is a pretty small angle, so we're going to have to change that to cosine 60 degrees minus 45 degrees. We're going to have to use a difference formula. And so cosine 60 minus 45 is going to be cosine 60 degrees times cosine 45 degrees. And we'll have to bring this down. And then minus, actually plus, sine 60 degrees times sine 45 degrees. So let's go back over this and make sure we did everything correctly. All right, it looks correct. So cosine 60, that's equal to 1/2. Again, you can draw a triangle if you want to, but if you can do it in your head, that's best. Cosine 60 is root 3 over 2. Sine 45 is 1 over root 2. We have 30, 60, 90 triangles that we're dealing with, and 45, 45, 90 triangles. So we're going to multiply these yellow fractions together and the blue fractions together. So the yellow fractions would be 1 over 2 root 2. And the blue, if we multiply, we get root 3 over 2 root 2. Now notice that we have a common denominator, a green common denominator, so we can add those fractions. So we get 1 plus root 3 over 2 root 2. So the biggest issue at this point is that we have a complex fraction. We really don't like complex fractions. So there's a lot of different ways to do this, but probably the easiest way is to treat this fraction symbol like a division operation. This is the easiest way for students to understand, but it's not very quick. It's not a quick way to do the problem. So let's shrink all this so I can find some more room. So when you divide by a fraction, you change to multiplication and flip the fraction. And now we're just multiplying that fraction by 1. So after multiplying by 1, you can see that we pretty much have the answer. Now the answer technically is not rationalized. The denominator is not rationalized. So what you would do is multiply both sides of this fraction by 1 minus root 3, but I'm really not going to make you do that because that takes away the focus from the whole point of this problem. I'm just not going to make you do that at this point. Okay, so if you got that right, good job. If you had a little trouble with that, that's okay. That's normal. These problems are pretty challenging. So, see if you can do number 16. 16 should be pretty easy if you know how to do it. And when you come back, we'll do it together. Okay, we're back. So if you recognize that expression, that is cosine 48 degrees plus 40 degrees. We're using a sum formula, but we're going in backwards direction. It's not the same formula that we used up there, but pretty similar. And so we get cosine 88 degrees, and that's going to be your final answer. We would need a calculator to find the actual value. But it says do not use a calculator, so that's as simple as we can get for the final answer. Okay, if you got that right, excellent. Let's go to number 17. Number 17 is going to be a double angle problem. Again, if you get stuck, that's okay, but try 17, and when you come back, we'll do it together. Alright, we're back. We're going to change sine 2 theta to 2 sine theta times cosine theta. Why do we do that? Because we can't solve an equation very easily when we have a single angle and what we call a double angle. So now we have all single angles, which makes the problem easier to solve. I'm now going to well, there's a number of ways we could do this. I guess I'll subtract 2 cosine theta from both sides of the equation. So we get 0 is equal to 2 sine theta cosine theta minus 2 cosine theta. And then we're going to factor out a common monomial. Notice that we have 2 cosine theta here and 2 cosine theta here. So both terms have that factor 2 cosine theta. We're going to be left with sine theta minus 1. If you want to know why that works, just multiply this 2 cosine theta into the sine theta and you get this orange term, and multiply the green 2 cosine theta by this blue negative 1 and you get negative 2 cosine theta using the distribution property. So what this tells us is that 2 cosine theta can be equal to 0, or it has to be equal to 0 in order for the equation to work, or sine theta minus 1 has to be 0. That's the only way that this equation could possibly work. 0 times whatever that would be 0, or 0 times whatever that would be 0. So these equations must be true in order for our equation to work. So we're going to divide both sides by 2 over here, and we get cosine theta is equal to 0. Add 1 to both sides over here, we get sine theta is equal to 1. These ratios are going to correspond to collapsed triangles. So you need the graphs of the sine or cosine functions. Whenever you have collapsed triangles, you need to use those graphs. That's the easiest way to analyze the situation. So the cosine graph looks something like this. We want to know what are the angles when cosine is 0. 0 means it's crossing the x-axis. So we're going to find the points where the y values are 0. That's those yellow points. And for the sine curve looks like this. Again, if you have those graphs in front of you, it's going to be a lot easier to see what we're talking about. And we're looking for the points where the y value is 1, and there's only one point right there. So that's considered to be 1 and negative 1. So what are the values? Well, if you're looking at those graphs, you can tell that this point here corresponds to 90 degrees, and this point corresponds to 270, and this point here is 90 degrees. Maybe I should write it down here. So theta can be 90 degrees or 270 degrees, or theta can be 90 degrees, but obviously that's redundant. So those are all the values between 0 and 360. So the final solutions are going to be 90 degrees and 270 degrees. So if you got that right, good. If you had some trouble with that, that's okay. These are pretty hard problems. Alright, on to number 18. It says, prove that the following equation is true by converting the left side to the right. So we're going back to proofs. Now this is a double angle expression. And in the previous problem, we had sine 2 theta. There's only one identity for sine 2 theta. But there's actually 3 identities for cosine 2b. There's 1 minus 2 sine squared b, 2 cosine squared b minus 1, and there's also cosine squared b minus sine squared b. So which one do we use? Well, it looks like we're going to use cosine squared b minus sine squared b, because if we do that, the cosine squared b is going to cancel out. So do you see this cosine squared b and this cosine squared b, they actually cancel out. Let me write that a little better. So then you're left with negative sine squared b minus sine squared b over negative 2. You can combine those negative sine squared b's to negative 2 sine squared b. Negative 2 divided by negative 2 is, well, they just cancel out, and you're left with sine squared b, and that's what we're trying to prove, that the left side of the equation is equal to sine squared b. So if you got that right, excellent. Again, there's 3 different identities for cosine 2b. So we used this identity here. Okay, on to number 19. We have cosine 2x again, another double angle expression. So obviously we're going to have to use a double angle identity. Try number 19, and when you come back we'll do it together. Okay, we're back. So again, there's 3 different identities. Which one do we use? Well, over here and here we have the sine function. So we want to make this equation simpler by changing everything so that we only have sine functions and no cosine functions. So we're going to change this to 1 minus 2 sine squared x. And if we combine the sine squareds, 3 sine squared x minus 2 sine squared x is 1 sine squared x. And then we're going to add sine x to both sides, because we recognize this as something that resembles a quadratic equation. And we're going to subtract 3 from both sides. And this is something resembling a quadratic in standard form. Now let's let y equal sine x, so we can see what's going on here. We have y squared plus y minus 2 is equal to 0. You should recognize this as a quadratic. So remember, when you're factoring a quadratic, you want to ask what 2 numbers multiply to negative 2 and add up to positive 1 in this case. And the numbers are positive 2 and negative 1. So now that tells us that y can be negative 2 or y can be positive 1. But we don't care about what y should be. We want to know what x is. So we have to change y to sine x. And it's impossible for sine x to be equal to negative 2. Sine x cannot be less than negative 1 or greater than positive 1. But we learned in a previous problem that if sine x is equal to 1, then that means that x can be 90 degrees. That means that x is 90 degrees. That's the only solution between 0 and 360. So if you got that right, good. Okay, so go ahead and try number 20. We're going to convert the left side of the equation to the right to prove that the equation is true. So attempt number 20. When you come back, we'll do it together. Okay, we're back. So we can combine these two sine A's, but we can't combine this sine A because it's not sine A. It's sine negative A. So I'm going to change sine negative A to negative sine A. I can do that because that's one of our identities, the opposite angle identities. So now we multiply negative sine A times 8, and we get negative 8 sine A. Now we have like terms. Now we can combine 3 sine A minus 8 sine A is negative 5 sine A. Negative 5 sine A minus 2 sine A is negative 7 sine A. And that's what we're trying to prove. So if you got that right, good. Okay, again, we're going to try to convert this side so that it equals negative 1. You're going to prove that that equation is true. So go ahead and try 21. This is the last class that we did before this test. So you should have that identity memorized. When you come back, we'll do it together. Okay, we're back. If you recall, cosine B plus 180 is negative cosine B. So this is a pretty easy identity, actually. And let me see what color we used for that. So we used a greenish color. Cosine theta plus 180 is equal to negative cosine theta. Divide those, and we obviously get negative 1. So we proved it. So if you got that right, excellent. Okay. So we're going to prove that this identity is true using this formula here. So see what you can do. You're going to have to use your graphs because we have collapsed triangles. And when you come back, we'll do it together. Okay, we're back. So I'm going to use that formula cosine A minus B. But instead of A and B, I'm going to use theta and 90 degrees. So we have cosine theta times cosine 90 degrees plus sine theta times sine 90 degrees. Now, again, if you look at your graphs, and we have to look at the graphs because we have collapsed triangles. The cosine curve looks something like that. I'm not drawing this perfectly, but it's good enough. And so cosine 90 is there. What is the y value if x is 90 degrees? And obviously it's 0. So cosine theta times 0, that's 0. And then we need the sine curve, but we've done this so many times, I think by now you can probably remember that we did that already. I'm going to go ahead and draw it just so we know. So the sine curve looks like this, and sine 90 degrees is there. What is the y value? It's 1. So sine 90 degrees is 1. So cosine theta times 0 is 0. Sine theta times 1 is sine theta. 0 plus sine theta is sine theta, and we proved it. We proved the identity. So if you got that right, excellent. Okay, so let's go to the next problem. Try number 23, and when you come back, we'll do it together. Okay, we're back. So we can use the following double angle formula. There's three formulas for the cosine of a double angle, but we're going to use this formula because we have cosine B that's given to us. So let's plug that number in. So we have 2 times 2 over root 6 squared minus 1. And if we square 2 over root 6, we get 4 over 6. Because 2 root 6 times 2 root 6 is 2 times 2, which is 4, and root 6 times root 6, which is 6. Then you can reduce that to 2/3 and multiply by 2, and you get 4/3 minus 1. And 4/3 minus 1 is 1/3. So there you go. Now we don't have to worry about getting the wrong sign in our answer, because remember, when you're working with double angle formulas, you don't have to worry about quadrants or anything like that, because the double angle formula is going to take care of all that for us. If you're using a half angle formula, then that's different. You do have to worry about the various quadrants that the angles terminate in. Okay, so on to part 2. It says find the value of sine 2b using the double angle formula below. So we have to find sine b first. We don't have sine b. So it says b is in quadrant 4, or it terminates in quadrant 4. So I'm going to draw an angle that terminates in quadrant 4. And that's going to be b. And cosine b is 2 over root 6. So 2 over root 6, and this is going to be positive 2 because that side is to the right of the y-axis. And now we're going to have to use the Pythagorean theorem to find this missing side that will allow us to find the value of sine b. So we have root 6 squared is equal to 2 squared plus b squared. And if you do the math, you end up with plus or minus root 2, but we know that b has to be positive root 2. Actually, it's going to be negative root 2. Because we can see that this side is below the x-axis. So then we can write that in. So negative root 2. So now we can easily calculate sine b. So sine b is the opposite side of the yellow reference angle, negative root 2 over the hypotenuse, which is root 6. And then we're going to multiply that by cosine b, which we already have. That's 2 over root 6. They gave us that in the original part of the problem. And then we can just multiply, and we get negative 4 root 2 over 6. And that reduces to negative 2 root 2 over 3. Now again, we're using a double angle formula, so we don't have to worry about whether or not the sign is correct. That's only with half angle formulas. The double angle formula does all that for us. So if you got that right, excellent. Okay, go ahead and try number 24, and when you come back, we'll do it together. All right, we're back. So we need to use a half angle formula. So this is going to be 1 plus cosine omega over 2. And the first thing we need to do is figure out if we're going to use the positive symbol or the negative symbol. So to do that, we need to think about the quadrant that omega terminates in, and it says it terminates in quadrant 3, and omega is between 180 degrees and 270 degrees. So that would be this quadrant here. So they're telling us that omega must be between 270 and 180. So what that means is if we divide, then we're going to go into quadrant 2. So omega over 2 has to be between 270 divided by 2. And probably should show that. So I'm going to divide both those numbers, 180 and 270, by 2. And we get 90 and 135. So omega over 2 has to be between 90 degrees and 135 degrees, which means that that's going to terminate in the second quadrant. So is cosine going to be positive or negative in the second quadrant, the green quadrant? Well, cosine is at the adjacent side over the hypotenuse, so the adjacent side has to be negative if we're in the second quadrant. So we're going to get rid of that plus sign, and cosine omega, they actually gave us that. That's going to be negative 3/5. We got that from here. And 1 minus 3/5 is 2/5. And if we simplify that complex fraction, we get 2 over 10, which is 1/5. And using our root rules, we then get 1 over root 5, and if we multiply both sides of the fraction by root 5, we rationalize the denominator, and there we go. So that is our final answer. So if you got that right, good. Okay, so now we're going to find sine omega over 2, and there's two ways that we could do this. One way is we could use the half angle formula, and that's the same formula you see here. It's just 1 minus cosine omega. But another way we could do it is we could draw the angle and just use the Pythagorean theorem. We don't want to have to do all this again, so we'll try the second method. So I'm going to draw omega over 2, some hypothetical triangle. So this is going to be omega over 2. And we know that cosine omega over 2 is negative root 5 over 5. We just found that. Or negative root 5 over 5. So we just have to find the missing number for the angle. So we can use the Pythagorean theorem. And we have 5 squared and negative root 5 squared. And if we solve, we get b is plus or minus 2 root 5. And you tell me, is b going to be positive or negative? Well, obviously it has to be positive because it's above the x-axis. So we have 2 root 5. And we can write that in. And now we can find sine omega over 2. That's just the opposite side of the reference angle. The reference angle being the purple angle divided by the hypotenuse. And we're done. So if you got that right, good job. Okay, so go ahead and try the last problem. And when you come back, we'll do it together. Okay, we're back. So we're going to have to use a half angle formula. And when we have sine, it's going to be 1 minus cosine alpha over 2. First thing we need to figure out is it going to be positive or negative? So to do that, we need to use some basic arithmetic. It tells us that alpha is in quadrant 1, which means that it's between 90 degrees and 0 degrees. So if we divide alpha by 2, we get 45 degrees and 0 degrees. So alpha divided by 2 must be in the first quadrant also. Is sine going to be positive or negative in the first quadrant? Well, of course it's going to be positive, because if you draw a triangle, sine is opposite over hypotenuse. The opposite side must be positive because the triangle's in the first quadrant. The opposite side is above the x-axis. So now we can plug in cosine alpha, but the problem is we don't have cosine alpha. So that's another thing that we need to do. We need to find cosine alpha. So let's draw a hypothetical triangle. And this is going to be alpha here. And sine alpha is root 5 over 3. And we can just use the Pythagorean theorem to find the missing side. So we have 3 squared is equal to b squared plus a squared. And if we do the math, we get plus or minus 2. But because the triangle's in the first quadrant, the angle terminates in the first quadrant, we know it's going to be positive 2. So that missing side is 2. So now we know that cosine alpha is 2 over 3, because we have that side that was missing. And 1 minus 2/3 is 1/3. And then we have 1 over 6, which is root 1 over root 6, which is 1 over root 6. Multiply both sides by root 6, and we get root 6 over 6. So if you got that right, excellent. Okay. So go ahead and try part 2. And when you come back, we'll do it together. Alright, we're back. So we know that alpha over 2 is in the first quadrant. There's multiple ways to do this. We could change this to 1 over cosine alpha over 2 and use a half angle formula, but we don't want to have to do all this stuff here. So let's just draw a hypothetical triangle in the first quadrant. And we'll call this alpha over 2. And we know that sine alpha over 2 is root 6 over 6, because we just found that. So now we can use the Pythagorean theorem to find the missing side. So 6 squared is equal to b squared plus a squared. So we get plus or minus root 30. And of course you can see just by looking at where the triangle is, it has to be positive 30. Positive root 30. So now secant is the hypotenuse divided by the adjacent side. If we multiply both sides by root 30, then we get the following. And 6 over 30 reduces to 1 over 5, and that is our answer. So if you got that right, excellent. Okay, so if you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And screenshot number 2. And number 3. 4. 5. 6. 7. 8. 9. And 10. But don't go before you get your homework. Let's take a look at the homework. Here's screenshot number 1 of the homework. And screenshot number 2. As you can see, the homework is a practice test. Screenshot number 3. And number 4. Number 5. Number 6. Number 7. 8. 9. And 10. But don't go before you get the answers. Now this practice test is not an option, it's mandatory. You must do this before taking the actual test. Here's a screenshot number 1 of the answers. And screenshot number 2 of the answers. So be sure to get that practice test done completely and correctly. Do not take the test in the next video unless you have done this practice test correctly, as well as the in-class test that we did. So get that test done, and I'll look forward to seeing you in the next class.